Well, all right, AP, chapter 20. We finally made it to my favorite chapter. We saved the best for last, okay? Electrochemistry is that topic that just made sense to me. It probably made my love for chemistry grow even more because I understood it and how it connected to the other topics like oxidation numbers and redox and net ionic and types of reactions and thermodynamics for delta G and delta H. It just made sense. And I think if it wouldn't have had to have been for this topic, seeing it in college, I actually did research with this topic with my professor my senior year, and it definitely is the love. Okay, so I hope you love it too. It is not an easy topic, but I think you're going to like it, and it's great review. We need this. It's great review from chapter 4. Okay, and we just got done with thermodynamically favored. So let's begin. 20.1 oxidation numbers. So here's where chapter 4's review comes. Electricity powers much of modern society, and I just brought in a little bit of history here of why electrochemistry is so important to our society, especially today. Extremely important to our society, but has like some big shortcomings. Okay, so obviously has some faults. It can't be easily stored. Okay, so we know electricity has to be stored in some type of container, a structure. That electricity flows into powers company lines and then consumes it and then gets regenerated. That kind of sounds like a topic we did before about, gets produced and then regenerated. And let's see if you can remember. Electrical energy is converted into chemical energy, which can be stored and is portable, like batteries, cell phones, laptops. There it is. You're doing electrochemistry all day long. You don't even realize it. It's in the power of your hands. And then converted back to electricity when you need it. Laptops, cell phones, pacemakers, not that probably any of you have a pacemaker, cordless power tools, wrist watches. That's a tongue twister right there. Currently, researchers are trying to develop new batteries. I just saw in the news last week about how this area in Nevada has so much lithium salt. And I'm sure you've heard of lithium batteries and how lithium batteries is the way we're trying to go, the way for the future. And definitely a much more efficient battery, and it's not even that costly either. Okay, so definitely was really cool when I saw that in the news because I was like, man, we're getting ready just to talk about electrochemistry. It's cool. Even they're going to try to use those lithium as in the power electrical cars. So this is where oxidation and reduction reactions happen. It's in those batteries, okay? There's a reason why batteries have like this, one side is plus and the other side is minus, and you have to put it in that device a certain way or it doesn't work. There is a huge purpose to that, and it's in this chapter. Chemical reactions in which the oxidation number of one or more substances change are called oxidation reduction reactions, redox, as we did in chapter 4, okay? Electrons are transferred. It's all about that. That is the key part right there. It's not that a substance lost or gained some type of crazy protons or neutrons. It's the electrons that get moved around. So the point of electrochemistry, the point of redox, and that is the word that usually you'll see on AP tests, it's about how those electrons move from one substance to the other. So did something get oxidized or did something get reduced? Okay, so redox is not just in the operation of batteries, but it also is rusting. Anytime something is surrounded by oxygen, it will rust over time. The browning of foods, those bananas that just go bad on you fast. And it also happens in the respiration of animals. So see, even biology is doing a little bit of redox in there too. So the point of these redoxes, you have to make sure if you have a redox reaction, there has to be somebody reduced and oxidized. You have to have at least one of each. Can you have more? Absolutely. But redox, oxidation does not go without reduction. It has to happen both in the same equation. So ladies and gentlemen, if they ask you if this is a redox reaction and why, you have to make sure you find who was oxidized and who was reduced. Because if you don't have one of each, it's not redox, okay? So you have to have need at least one substance that was oxidized and one substance that was reduced. Okay, you have to have at least one. I have seen equations, and you'll see them in the book, where you actually have like 2 oxidations and 1 reduction, and that's okay. But you got to have at least 1 and 1. Where we remember redox, remember our Leo the lion, okay, loss of electrons from one substance is oxidized, okay? And what Leo says is not roar, but my lion, Leo the lion, says grrr and gain. You know you're going to miss me, ladies and gentlemen, my crazy little, what are these called? Oh my God, I had a brain fart. What are they called? Anagrams? I don't know. Well, whatever. You can ask Rojas. I'm sure she knows the word. All right. So Leo the lion, loss of electrons, grr, oxidation, and my Leo the lion, grr's gain, electrons reduced. But this is also the part that students forget. What happens to the oxidation number between one to another? Okay, so right here, I'm just take a little break from this part right here. I'm going to do an example with you on the next page, and then we're going to come back to this. It's not just losing and gaining electrons, but AP can ask you what happens to the oxidation number from one side to the equation. Okay, so one side of the reactant to the product, did that oxidation number increase or decrease? So we need to make sure we understand that. Now let's go back to review those oxidation numbers. So I'm going to try to put a couple examples down here to go with them. Let me find my examples. Okay, all right, I think I found them. Okay, so electrons are not shown in chemical equations. And what I mean by this is the overall balanced equation. You will never see the actual electrons in that equation. However, you do see the electrons. They do appear in what's called half reactions. Okay, and this right here, you're going to see it in 20.3. Okay. So actually, you're going to see it in the next one, 20.2. Okay, so 20.2. Oxidation numbers, or oxidation states, help us keep track of electrons. Did the electrons get lost in the reaction, or did they get gained by somebody else? So rule number 1, there's a lot of rules, and I know they're going to all come back to you. You'd be like, all right, Rodriguez, I remember this. I just need some practice. See, I know what you're saying. Elemental form. And you know you've seen that word big time lately. Elemental form, the oxidation number is always zeros. Think of it like delta H, okay? So I'm going to put right here, like delta H and delta G. We don't need to look it up because sodium as a solid is 0. Chlorine diatomic, as long as it says gas, is 0. Even like iodine, as a solid, make sure you know those halogens, what state of matter they're actually elemental natural form. We don't look them up because they're always 0. For any monoatomic ion, the oxidation number is the charge. So if I actually slap on a charge on that sodium, well, now it's +1, okay? Or if I put the charge on chlorine, it's actually -1 now. You physically have to see the charge on paper. Okay, so right there. Nonmetals usually, okay, and you know I cannot say that word negative. However, with oxygen, it's usually -1. But be very careful with peroxide. With peroxide, it would be -1. Sorry, oxygen is usually -2. I think in my head I even said -1. In my head I said -2, but I think verbally it came out -1. Okay, rewind here. Oxygen is usually -2, but in peroxide the oxygen is -1. It's because when you're doing the purpose of oxidation numbers, it's that value for one of the elements in that form. If you notice right there for oxygens, I have 2 oxygens. I have 2 of these that have to equal -2. Well, what if just one of them? Well, one of them is -1. So 1 is -1, okay? But if I had oxygen, as in like this, okay, like oxygen and water, then it would obviously be the -2. So with peroxide, ladies and gentlemen, because there's two of them, the total is -2. But for one of them is that -1, okay? So this is only applying for peroxide. Hydrogen, usually +1, when bonded to nonmetals. So if I would have my HCl, I know the hydrogen's +1, the chlorine's -1, okay? Because you're going to remember the sum of the oxidations have to equal 0, okay? There is a but part to this, but we'll get to it. But what if I put this -1 bonded to a metal? So most of the time we usually see like hydrogen with like the alkalis, and you would see the hydrogen in the back. So we know metals have to be positive, okay? Metals are positives. All metals have positive oxidation. But see right here where it says nonmetals, usually you're going to see some nonmetals go positive on you, okay? So sodium right here is +1. The hydrogen in the back, because right here this is called hydride, not hydrogen. This is hydrogen with chlorine. This is sodium with hydride. That hydrogen's -1. Okay, so only oxygen and hydrogen, you got to know the little flip-flopping tricks. Halogens have oxidation numbers of -1. Okay, so if you are trying to figure out which one is which, we usually put the halogens as the -1, and then the other nonmetal can be whatever it is. If you do have a polyatomic, okay, the polyatomic has to equal the charge. So like for example, one of them that I'm going to do with you, let's see, like manganese, okay, with oxygen, that's permanganate. The oxidation number has to equal that charge. So when I figure out manganese and I figure out oxygens, the total has to equal -1, not 0. Okay, so in this case, I don't know anything about manganese. They can be anything, but I do know oxygens. Okay, because oxygen usually -2. I don't see peroxide, so I know it's not -1. So -2, and then we're going to times it by 4. That equals -8. Well, it has to equal -1. So manganese has to be +7. So what are you telling AP is the oxidation number for oxygen? It ain't -8, because that's the total oxygen. I need the oxidation number for one of the oxygens, not all of them. The total is just to help me with the math. So if you have just a regular normal compound with no charge on it, I'm trying to find you an example one. Like, okay, I found one right here. Sodium iodate, okay? Now I know that's a polyatomic, ladies and gentlemen, but if you saw parentheses, you would want to do the polyatomic part separate, okay? And I don't need to do it separate here because I know sodium, and I'm going to be adding some rules to this too. Sodium +1, okay? Oxygen, -2, and then that 2 times 3, -6. Well, that's his oxidation numbers, but this is to get me to the math, okay? Now, halogens usually, there's probably supposed to be the word usually there too, oxidation -1. However, in this case, iodine is not going to be -1, okay? Because I know oxygen is -2, I know group 1 is always +1, and this iodine right here has to be +5 because I need it to equal that 0. So ladies and gentlemen, in chapter 20, that's kind of like a shortened version of what oxidation numbers were. But if you go to, I was just pulling it up right now, if you go to chapter 4, right here, and this is in section 4.4, these are very detailed rules, okay? Because I'm also even noticing in chapter 20, there should be a rule about all group 1 metals, like sodium, lithium, potassium are always +1, and all group 2 metals are always +2, okay? But there is a rule about the halogens, and I know I included it in here, right here. The oxidation number of halogens, or right here, the oxidation number of fluorine is always -1. The other halogens are usually -1, okay? But when chlorine, bromine, or iodine is bonded to oxygen or fluorine, it will have a positive number. So right there, that is the more detailed example of the oxidation numbers, okay? So trust me, see how we practice a ton of oxidation. So you'll want to go back, ladies and gentlemen. This is more of a very Cliff Notes version of it, very, very brief. But please review. Get a little red going on. You know, Rodriguez in the red. Read your 4.4 rules of oxidation numbers, okay? Because we definitely need that review. Electrochemistry is that branch of chemistry that not only deals with electricity, but how does it affect the chemical reactions with electricity. And like I said, it's about the moving of those electrons, how those electrons move from one substance to the other. So electrochemistry studies whether a reaction will be spontaneous or not, thermodynamically favored, okay? So will that delta G be negative, or will that delta G be positive? Okay, it brings in the thermodynamics with electrochemistry. Okay, it brings in oxidation numbers with the electrical chemistry. It brings in types of reactions. This is the chapter that should tie it all together. It should be that chapter like, oh my gosh, I know now what I should have been doing back in September and October. It's that chapter that really, really, really needs to tie it together. Or we got some bigger issues to deal with, ladies and gentlemen, these last couple of weeks. So here's an example of how you will see an equation where you will see charges in it and whatever states it matters and so forth, so forth. So consider the thermodynamically favored reaction of zinc with HCl. Now you don't see the Cl part because what happens is that's probably a spectator ion. So spectator ions, they're just watching the show. They have no purpose in the overall equation, but they are there to help with the chemical balance equation part. Okay, they're just not a major player. So let's go through all the oxidation numbers. So if I have zinc by itself, normal, elemental, solid, because all metals are solid except for one, that means it's the oxidation of +1. The oxidation number of this hydrogen, because I physically see a charge on it, is +1. Now this 2 is here to balance the equation over here, okay? So this hydrogen, elemental hydrogen as a gas, is 0. And I see this charge on zinc, that means it's +2, okay? So what happened here? I always like to kind of like branch it like this, group it together. I know that I had pure neutral zinc where the protons and electrons equaled each other. But now over here, I have +2. I lost 2 electrons. I was perfect in the beginning, and now I lost 2. So that means right here, that zinc, it increased the number from 0 to 2. Okay, so remember when I said, be very careful if AP asks you what happened to the oxidation number. So for example, that zinc solid went to zinc +2. Well, it was neutral, and then it went to +2. That is an example of oxidation number has increased. I went from 0 to 2, okay? So, for example, with the hydrogen, let's go in a different color, a little Christmas going on here. Well, I have +1, and I went to 0. I went from 1 to 0, okay? So that 1 to 0, I know that I gained an electron. And I know you're like, wait a minute, Rodrigo, okay, what? Okay, you have to remember, in the beginning, it was already missing an electron. It was already missing an electron, and it did a chemical reaction, and now it went back to elemental form. And now when it has elemental form, that means my protons and electrons, they equaled each other. I gained an electron. So in that case, the hydrogen decreased its oxidation numbers from 1 to 0. Okay, it went from 1 to 0. So let's get that example down too. So the hydrogen +1 went to H2. We'll put a 2 right there. And that went from +1 to 0. So my oxidation number decreased. It's not, ladies and gentlemen, just telling AP that zinc lost electrons and hydrogen gained electrons is what if they ask you about how did the oxidation number change? Did the oxidation number increase by this to this, or did it decrease by this to this? Okay, so oxidation, loss of electrons, gain of electrons. I've even had a student back in the day say like oil rig, oxidation involves electron or loss of electrons. Reduction involves gaining electrons. Okay, you can use whatever one you want, but I still like my Leo the Lion. Okay. So in order for this to be a redox reaction, somebody had to be lost and somebody had to be gained. So the zinc was oxidized to that zinc plus 2, and the H was reduced to that H2. Okay. So the hydrogen caused the zinc to be oxidized, and the zinc caused the hydrogen to be reduced. You have to go hand in hand. That's why, ladies and gentlemen, you have to have one of each, because they are partners in that whole balanced equation. Okay, it's like a dance. Okay, unless you're dancing by yourself or dancing with a partner, okay, in order for it to be a partner, you have to, somebody's leading and the other one is following. Okay, it's kind of like oxidation reduction. Somebody's doing some of the work, and because of that work, it led somebody to do something else. Okay, so let's try a couple more oxidation reductions. You're going to see in my notes, and I want to make a little AP thing. You're going to see stuff in my notes because I took it out. I'm editing my notes like slowly so I can get them all to look beautiful like the other chapters. Oxidation agents or reducing agents are not tested on the AP test. So that's why anything in the notes that you saw right here that had to do with oxidizing agent, reducing agent, or something called the oxidant or reductant, not tested. So just put like a big old black Sharpie. Now in college, heck yeah, they could ask that, okay? But we're not doing the college way right now. We're doing the AP way. So not tested on AP exam. Okay, so just make a note if you don't want to black it out with the Sharpie, because someday when you're in that chemistry class, you'll be like, you know what, Rodriguez, thank you. Thank you for these beautiful notes that everybody is flocking to. I know, you're welcome. But it's not on the AP test, okay? So that's why I took it out. Cadmium, let's figure out who is oxidized and reduced. Cadmium elemental form is 0, okay? Now, I know this nickel is going to be positive because it's a metal. And assuming this is not peroxide, because it could be peroxide. Let's just say it's elemental oxygen, usually normal -2. But you have 2 of them, which means it has to be -4. So it's got to be 0. The nickel right here, the nickel has to then be +4. So those are my oxidation numbers. If by chance, if that would have been peroxide, so if, because technically it could have been peroxide, I don't see a name on the paper, that right there would have been -1, and then that right there would have been +2. Okay, but let's see what happened on the other side. Water is always -2 +1 every single time. Okay, now what happens when you have polyatomics, especially in parentheses? Now, I always tell my students when you're doing these that you're probably going to want to have do the polyatomic part to the side. So if you see polyatomics, okay, pull it to the side, do it to the side. But when you're doing the polyatomic has to equal the charge of the polyatomic. So like for example, I see hydroxide twice. And I know hydroxide has a -1 charge. So that means when I do the math for this, it has to equal -1. Well, ladies and gentlemen, it's not rocket science. Oxygen's -2, hydrogen's +1. There it is. Okay, it's just like water. Oxygen's -2, hydrogen's +1. So now I know right there I have oxygen -2 +1. Same thing over here. -2 +1. So where the heck did this 2 come from? Well, hydroxide's -1, so that 2 must have came from cadmium. And the same thing right here. Hydroxide's -1, so that 2 must have came from the nickel. Okay, that's why I do not think it's peroxide, because look at right here. If it's peroxide, +2, +2. So in this case, could not have been peroxide, because if you notice, we needed that nickel to change. And if I said peroxide +2 to +2, it didn't change. So who changed? That's the question that you ask yourself. Who changed? Well, my cadmium went from 0 to +2. Nickel could not have been peroxide as in nickel, that +2. So this nickel right here, let me go in a different color. Nickel went from +4 to +2. Oxygen, -2, -2, -2, -2. Okay, so unchanged. I'm just making a little mental note. Oxygen didn't change. And hydrogen, +1, +1, +1. Hydrogen didn't change. We only care about the people that actually changed. So right here, cadmium went from 0 to +2. And right there, the cadmium's oxidation number increased. Okay, the oxidation number increased. And what does that mean if the oxidation number increases? Okay, well, go back right up here. The oxidation number increases. That means that substance was oxidized. Okay, so cadmium was perfect. And then over here, +2. Okay, it lost 2 electrons. Okay, so right here, my cadmium was oxidized. Okay, it lost 2 electrons. They may ask you on the AP test, how many electrons did it lose from one to the other? Okay, and we're definitely going to be practicing that. Nickel, let's go nickel. Nickel went from +4. He was already missing 4 electrons to begin with. He was already missing 4. But then he's now +2. He gained 2 of those missing electrons. So he was reduced, okay? And, oops, let's look at what the oxidation number did first. So right here from 4 to 2, my oxidation number decreased, okay? And in that case, I was missing 4 electrons, and now I'm only missing 2, so I must have gained 2 of those electrons and was reduced. Because I gained, not only did I gain electrons, but I gained 2 electrons, okay? Let's try another one right here at the bottom. Don't need to overlook water too much, okay? +1, -2, okay? Elemental aluminum, solid, definitely 0. Now right there, I have a polyatomic with a charge. So we already did this one right above. Oxygen, -2. But times 4, -8. I need that to equal -1, not 0. So in this case, a positive something, -8, -1. So right here, permanganate, that must be 7. So remember, these are the oxidation numbers. Aluminum right here, and then hydroxide. Well, we already know hydroxide is -2 + 1. And hydroxide has a total -1 charge, okay? So where did that 4 come from? Well, it must have came from that aluminum. And it's kind of freaky seeing aluminum as a +4 when he's usually a +3, okay? So overall, look right here, aluminum's +4. I have hydroxide is -1. Wait a minute, let me make sure I'm doing that right. -1 and 4. Oh, boo-boo. Wait a minute. Let's go back. Okay. I'm just going to talk to myself. All right. Hydroxide right there. Total charge is -1, but you have 4 of them. And it's got to equal -1 because of that charge. So I was doing it in my head with the 0. So that's -4, -1. So that aluminum, not +4, +3. I was going to say, I thought that looked kind of freaky seeing a +4. And then over here, I have manganese with oxygen. Now, assuming that's not peroxide, okay, well, I'm just assuming. Oxygen, -2 times 2. And then that means that manganese has to be a +4. So the question is who changed? Well, if you notice the hydrogens, none of the hydrogens changed. So I'm just going to put under here unchanged. So hydrogen didn't change. Oxygen, -2, -2, -2, -2. Okay. I didn't mean a 0, meant oxygen. There you go. Aluminum did a change. So aluminum from here to here went from +3, 0 to +3. And manganese, 7. Now you could have said that was peroxide, but you'd have to actually, If AP did not say the word peroxide, I wouldn't use peroxide, okay? But you would have to tell AP, assuming that was peroxide, that manganese then would have been +2, okay? But we're just going to think it's normal oxygen. So this oxygen went from +7 to +4, okay? And we already said oxygen did not do any change, okay? So aluminum went from 0 to +3, okay? That oxidation number increased from 0 to 3. And you were perfect aluminum. Protons and electrons equaled each other. And now you have 3 missing, okay? So it definitely lost 3 electrons. So that means he was oxidized. And right here, manganese went from already having 7 missing to gaining a couple to get to +4, okay? So that oxidation number went from 7 to 4. So the oxidation number decreased. So he was already missing 7 to begin with and gained a couple, but still +4. So he gained, how many did he gain? He gained 3. And it's not always the same, ladies and gentlemen, as this one. Lost 2, gained 2, lost 3, gained 3. It's not always that way. You're going to see why in probably the next video. And so that means that manganese was reduced.